Welcome again, and now we're on chapter 10, section 3, and that's about chords. And if you remember what a chord is, it is a segment that lies inside a circle that connects any 2 points of the circle. The largest chord, which is the one that runs through the center, is called the diameter. So right away, chapter 10, section 3 starts with theorem 10.3, and it says in the same circle or in congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So what they're trying to say, if chord BA and chord CD are the same, then arc BA must be congruent to arc CD. This arc here must be congruent to this arc here. So what type of problems can I do with that? Pretty simple. If I tell you that AB is I tell you the chords are the same, AB and BC are the same, I tell you that this is 110, then I would know that BC is 110. It would also allow me to find AC because we know that the whole circle is 360 and we could subtract 220. Please remember, again, when I'm asking for the measure of an arc with only 2 letters, you know they're asking for this arc instead of asking for this arc, because basically it could be BC going that way, but because it's 2 letters, it's still a minor arc, and that's how you know they want the 110 and not 250. All right, and if you look at the second problem, why don't you pause and try it? If AC is 150, then how can I find AB? Well, if I know they're the same, I can take 360 minus 150, which is our 210, and divide, and it's each 105. Okay, so pretty simple theorem. Chords are the same. The arcs that they intercept. If you're having trouble with intercepting, please note extend this, and it would be whatever's above that arc. Okay. The next theorem, which is 10.4, also combines theorem 10.5, and it says that if a radius or diameter are the same, if a radius or diameter is perpendicular to a chord, then the chord and its arcs are bisected. So if I look at this circle and I see that EG, which is the diameter, or from the center over, which is the radius, is perpendicular to chord FD, then HD and HF would be the same. So right here, simply saying F is 7. It also says that if they're the same, then this piece and this piece would have to be the same. So GD would be 40. Just be careful. Sometimes I'll ask for FD, which you would know is 80. So just be careful what I'm looking for. The theorem 10.5 just says that if these are bisected, if this segment is bisected and it's perpendicular, that it must be a diameter. So it's like the converse. So those 2 theorems are together. So let's look at this one. One thing we want to be careful, I can be a little tricky, because if I tell you that there is a radius value given, please note you could always have to draw a radius or put a radius anywhere. A radius is from the center to the edge, so it could be anywhere. So for example, the radius of the circle is 13. So most people are going to say, oh yeah, well I see QJ is 13, that's great. But you also can assume QK or QH is also 13. So let's look at what I really want. I want to tell you it's 13. I tell you QL is 5, so I do know this is 5. I would know this piece down here is 8. Might not be drawn to scale. And I want the length of HL and HK. Obviously, once I figure out HL, then HK is just double HL. And so what I do want to know is this is a radius. So I actually know that this is 13. I know this is 5, and I'm missing this piece, which is LK, or is the same as HL. So even if I went this way, it would be the same thing. This is 13. So it's a right triangle, as we see. So I'm simply going to run Pythagorean theorem, 13 being the hypotenuse. So on this, I'm going to get 169 equals. And I'm going to take the square root. I would get x equals 12 and negative 12, but negative's not going to be used here. So x is 12. That tells me that HL or LK is 12, and therefore HK is 24. Okay, these can get a little tricky at times, so we just want to make sure we're using right triangles and that we're using anytime given a radius that you can draw in a radius where you have to. And theorem 10.6 says this, that if two chords are congruent, if and only if they are equidistant from the center, okay, and I kind of have a problem. That's not even supposed to be here. Sorry. In the same circle or in congruent circle, two chords are congruent if and only if they are equidistant from the center. So chord AB would be congruent to chord CD if and only if EF is equal to EG. In order to be equidistant, we show you that they're the same, but we also show you that they're perpendicular, so that you know they're at the same angle, they're not leaning in or vice versa. So two examples could look like this. In this problem, I tell you AB, I tell you that the chords are the same length, and you see the perpendicular, so you're just simply going to set them equal. Sorry about that. I asked not to find x, but to find EF, and so it's 6. And in this one, just be careful. That's why it's kind of nice to have color, but I'm showing you that 3x plus 2 is only this piece, but I show you that this one's 22. We know that they should be equal in length because they are equidistant from the center and they're perpendicular, so it's actually going to be 2 times 3x plus 2 equals 22. Okay. And the last problems are just a combination of anything. So if you want to definitely try to pause this and find this on your own, go ahead, then come back to the video. Just in case you had any confusion, I just want to let you know that this is the piece that's 9. Yes, we know this is a diameter, so, I'm sorry, a radius, so we would know that's how much, 12, considering this is, but I can also put a radius here, and I know that this is 12, and now I know this is 9, and I know that's a 90 degrees. So I'm simply going to run Pythagorean theorem to find this little piece, which I'll call y. So I'm going to get 12 squared equals 9 squared plus y squared. I get 63 equals y squared. So y is, and for now we'll use decimals, it's 7.9. So now, if I clean this up a little bit, we know that this piece right here is 7.9. So if I put a 7.9 here, but I know this entire value is 12, 12 minus 7.9 is 4.1. So that piece is 4.1. Again, it's just trying to realize that if I give you a radius, please be advised you can put the radius anywhere you need to. in order to solve. And the last problem is 3 problems, trying to determine from the theorems, is it enough to say that AB is a diameter or is it not? In the first one, it is perpendicular and it's bisected. So if this is bisected, meaning each piece is 6 and it's perpendicular, then AB is definitely a diameter. In the next one, I tell you these chords are congruent, which is great. That tells me this and this are congruent, but it tells me nothing about AB being perpendicular. It tells me nothing about CD having to be bisected or anything else. Yes, the angle's bisected, but that does not tell me anything. And then C tells me, yes, they're perpendicular, which is great, but this piece is 3, and if I look at this right triangle here, and I realize it's a 3 missing and a 5, I can run Pythagorean theorem, and that's our pretty famous triangle. It's going to be 25 minus 9, which is going to be 16x squared. It's going to tell me that's a 4. So even though it's perpendicular, you have to kind of realize it's shifted over AB a little bit, so it's definitely not a diameter, so it is not in this one. And this would be your justification, or you would just say that no, because it's not bisected. All right, thanks. Hopefully we can work on some of the problems from this section now too.